Today we're going to talk about the multiplication rule. And I don't know if you remember one of the problems that you did in the stuff you did on Friday had a multiplication rule, but I said we would get to that one. Okay, here's the easiest way to remember this. If you have to do two things together as an and, this and this, and you put parentheses around it, and remember that you used to multiply and put parentheses around your things, right? So that tells you you're going to multiply these guys. The or tells us we're going to add them. But the and says I need both of these to happen at the same time. So we're going to multiply these. And also, you have a little issue if it's dependent or independent. For a dependent event, this one is multiplied by this after it's dependent on this one. For an independent event, it has no other concerns. We just take them and multiply them. You'll see the difference. The multiplying them with an independent event is basically the same thing. You're just going to have to change your probability for this one. This one says your probability might have changed a little bit. So let's take a look at an example. Two cards are selected without replacing. Is that independent or dependent? Dependent. This is dependent because your probability will change. The total number of cards will change, right? Right there? Is that good?
Yeah, I'd say it's 51 left.
You have 51 left.
It's a Monday.
Well, first one you take is 52, then 51. Okay, so we want to find the probability of selecting a king and then a queen. So remember, we're not replacing this. This has this effect, but you don't even really see the independent part because we're just going to take it out of there.
Is it 452 and 451?
Yes. So hang on to that thought. 1 second.
I'm sorry.
No, that's okay. It's generally this case, and as Darian said, you have 4 out of 52 choices, and if we keep one, we have 4 out of 51. Now your multiplication rule says just multiply them. And when you multiply the tops, and you multiply the bottoms. And that would be 2, 6, 5. Don't forget to multiply across, top and bottom, numerator, denominator. You can actually just do it in your calculator. You can break this down to a decimal. If you're going to do a decimal, give me 3 decimal places. If you go to a decimal, okay? Question?
The number on the bottom, is that 2,652?
52. We multiplied 52 times 51. This guy forced it to change. Now, the difference between this being a dependent event and an independent event would say no replace. And it basically is going to look the exact same. Probability of a king and a queen, the process is going to be the same. 4 out of 52, only now since we're replacing 4 out of 52. But we're still going to multiply. So the fact that it's independent or dependent is reflected right here in this second one. Go ahead. This is if we replace the card. This is a dependent event because we're keeping the card. We changed the probability. This one is the exact same setup, only now when I see my king, I'm going to put it back into the deck. I'm going to replace it. But we're going to still multiply. The multiplication rule still holds. The only thing that changes is this piece right there. Yes. Go back.
16 over 2,740.
16 over 2,740?
4. 207.
And 4. Okay. All right. Questions on this? No? I'll just pencil right on my table right here. Okay. Let's see if this is going to scroll with me or not. No. All right. So, I'm going to toss a coin and I'm going to roll a die. I'm doing both of these things in one event. I want to find the probability of getting a heads on the first time and rolling a 6. Is this independent or dependent? Independent.
Yes.
Yes, because your probabilities are not affected. Rolling a coin, tossing a coin, rolling a die has nothing in common. One does not affect the other. So what is the probability of getting heads on one toss?
Half.
A hat on one flip. What is the probability of getting a 6 out of your die? 1 out of 6. And what am I going to do with these guys? Multiply them. Multiply across and across. Okay, now there's no way to make that one a dependent event because they're both completely opposite. Okay, you guys try the next two. You try the next two. Page 132.
Hey, did you get a new calculator holder?
Yes, I did.
Yeah, I noticed it.
See that?
Girls like it, you noticed it because.
Yes, guys, pay attention to that. So give this one a try. Think if it's dependent or independent. This is page 132. Okay, so for the first one, we're looking for the probability that one salmon swims successfully and the second salmon swims successfully. Is this independent or dependent?
Independent.
Independent. So what are we multiplying?
0.85 times 0.85.
Good.
You get
And?
0.7225, which equals to 289 over 400.
You get, what did you get for your decimal? Point.
7225.
Thank you. You can leave it as a decimal. Now remember, the and, put it in parentheses like this. You need this and this. And remember when we used to multiply things like this, we would just put them in parentheses. So whenever you see parentheses around it, this and this is being in one. When we do an or, they're going to be two separate sets of parentheses. So one parentheses says multiply. The next one, two cards are selected from a standard deck without replacement. So does this make this dependent or independent? Dependent. So your probability is going to change on the second card. So I want the probability of a heart and then a second heart. So first time around, what is the probability of a heart?
13 out of 52.
13 out of 52. Second time around, I'm keeping that heart. What's the probability of a second heart? 12 over 51. Good. One less heart, one less card. One more. But that's okay. Yeah. Sure can. Okay, no problem. Okay, you got a pen? Simran, if you could see Miss Jones at the end of each area, two seconds. Okay, so we multiply these guys. And if you want, you could leave it as a decimal and make life easy. Okay, everybody's good with that? Okay. We're gonna find the probability of getting, again, we're just tossing our die. We're gonna find the probability of getting a head and then rolling a 2. Okay, so the same basic setup we did before. Probability of getting a heads and getting a 2. This has to be done in one event. So it's like a compound event type thing. What's the probability of getting a heads when you flip a coin? getting a 2, rolling a 2 on your die. And what do we do to these two? Add them or multiply? Multiply. The and says multiply. 1 out of 12. Okay? And the probability that 3 swim through would be your 3.
The same thing is zero point
I'm sorry, say that?
the same thing is 0.3 or 1.5.
For which one? For the one we just did? 112. It was the exact same thing.
Oh, it was the exact same.
Well, no, it was a different question, but the same scenario: a head and a flipping a dice. So flipping a coin, rolling a dice gives you the same type outcome because your probability is not changing there because it's independent. So nothing changes. It's still 1/2, 1/6. So right. So that's what that was kind of meant to say. How about the probability that a salmon swims successfully through a dam is 0.85? Find the probability that 3. We want the probability of 1 successful and another successful and the third successful. I want the probability of 3 successful salmon. Is this independent or dependent?
Independent.
Independent. So what's the probability that the first one gets through?
0.6141.
Okay, so 0.85.
Oh, right.
So 0.85, what's the one with the second one? 0.85.
That was 0.85.
Right. Or decided not to work.
I was answering the question.
I'm sorry.
0.85. Well, okay, so 0.85 times 0.85 times 0.85. This is independent, right? Right.
I'm sorry, I should take into consideration. I'm sorry. I made a mistake.
Okay? And you multiply them. That's the same as 0.85 raised to the third power. You have 3 of these guys. So 0.85 times 0.85 times 0.85, the same as this. Okay. How about
What?
raised to the third power?
So you just leave it like that?
You could, well, no, you put it in your calculator. And what'd you get? 6.614?
Oh.
Give me 3 decimal places. I want 3 decimal places on your probabilities. Because what happens is you can't round them too close because if I round it down, especially on one that's half, like 0.52 something or other, you don't want to round it down to 0.5. You're telling me it's exactly half, which it's not. Probability has to be a little bit more exact. Find the probability that none of these are successful.
I got 3
So how'd you set this up?
0.15.
To the third, good. Each one of them has a chance of not making it through as 0.15. This is your complement condition. So again, Lizzie, what'd you get for that?
0.003.
Thank you. 0.15 to the third. Because we use the complement. If they get successfully through, all your probabilities have to add up to 1. So the only other choice they could be is not successful. So 1 minus 0.85. That's your complement condition. And we see that quite a bit. Your complement. So let's just take a look before. We had this as 0.003, that none. 0.614, that 3 of them. We got through. Now it's asking me, find the probability that at least 1 salmon is successful in swimming through the dam. Well, we have 2 conditions right now. We have one where all 3 went through, and we have one where none went through. So if I want at least 1 to go through, how can I do that?
0.85 times 1.5 times 1.5.
So 0.85, okay, let's take a look at this. 0.85 times 0.15 times 0.15. Does it matter what order that they go through?
No.
No. So this would work if the first one is successful, but the other 2 aren't. What other conditions can exist?
First
It
two
says
are
at
equal.
least so all.
So all 3 could go through. Or let's look at all possibilities. So 0.15 times 0.15 times 0.85. What's another possibility?
Wait, isn't that the same thing?
Yeah.
It's going to give you the same results. But this tells me my first one got through. This tells me my third one got through. So can I be here for a while? And it says at least. So can I also have 0.85 times 0.85 times 0.15? Can I also have 0.85 times 0.85 times 0.85? Ah. So what could I do instead? No, think about it. This is your complement case.
Because one minus 0.85 is 0.5.
So what do all your possible probabilities add up to? 1. All your probabilities add up to 1. What is the one condition that I'm not going to list here?
None of them.
0.15, 0.15, 0.15.
Correct.
Okay, we're getting to it.
It's not there.
So I could sit here and list all the possible things that could happen, right? The only thing that I'm not going to list, as Elvis said, is 0.15 times 0.15 times 0.15, because this is not at least 1. This is the only condition that defies that one, that says, oops, you didn't give me at least 1. So instead of doing this, and we could be here a while doing this, we're going to do 1 minus this condition. We're going to use its complement case. We could stay here for a while and find every possible one, and we could do it. It's not too bad, because at least 1 says it could be 1, it could be 2, or it could be all 3, but it could be any order. So I have to sit here and go through each scenario. The only one that it cannot be is, like Elvis said, this one. That's not at least 1. That's none. So if I subtract 1 minus that condition, I will be okay. So 0.997. The probability, don't forget, the probability that 1 swims through is very high. It's high. So the probability that at least 1 makes it has to be very high, out of 3. If you say at least 1, you could have 1, you could have 2, you could have all 3. You could also have them in any order. That adds to our situation. So the only thing that cannot happen is that they all 3 failed. Your sum of your probabilities always add up to 1. All possible things. So therefore, we'll just take the shortcut and use our complement case. Make sense? Okay. We're going to try the next 2. Yay. You guys try the next 2. It's got the same type of situation, so I need you to think about it. Page 133. Do you also remember doing this in Algebra 2? The other one we did with the C? Do you remember doing it at least one when we did this with the C? 0.85, how many we wanted, 3 things, 1 at a time. And we did this. Remember doing those? It's kind of, this is why you did this. This C, that could be in any order.
You had to do like a really long thing with that, right?
No, well, you had to do, like, if it's at least 1 out of 3, you had to do a 1, or a 2, or a 3. The only one you weren't doing was the 0. You had to do it 3 times, but you could just plug them in your calculator. But the idea is that this combination gives you 3 times this. That, in other words, you could be successful first, second, or third time. That's what the three, the combinations did on yours. So the probability that a salmon has now increased to 0.90. What's the probability? How do I set this up? That 3 salmon swim successfully through the dam.
0.9 times 0.9
0.9 times 0.9 times 0.9, or 0.9 cubed. And what did you get?
0.729.
Okay, thank you. Find the probability that at least one salmon successfully swims through. Okay, so 1 minus this guy. One, it's the same as the other one.
No,
No.
because in the other one we subtracted
You did
the
the
opposite.
complement.
The compliment.
Yeah.
But
That's not a compliment.
I thought it was.
Wait,
I thought it was 0.001.
Your Monday mornings are worse than ours.
Yeah, I think so.
It's times 0.10 times 0.10 times 0.10. And then whatever that equals minus 1 minus 0.10.
At least one.
Yeah, it's 1 minus
You did that one.
Point
with
zero,
0.10.
zero,
Wait, hang on.
It's not a drug.
Find the probability that at least one successfully swims through the dam. Okay, so the only thing we want is when they all do not. You're right. When they all do not. So 0.1 times 0.1. Good job, guys. You got
I say we're not gonna
That's
test this
very
again.
good. Okay, so what is 0.1 times 0.1 times 0.1? Or 0.1 0.001. I should have listened to Ben. He was talking right in my ear here. Right, Ben? 0.999. So, first of all, did that probability increase from the last one we did?
Yeah.
What made it increase?
The percentage of you taking
The higher percent of them swimming through, right? There's a higher percent now of them swimming through. Good. You guys got the compliment case. Very good. When we do the one with the combinations, we're going to do those again in here. We're going to set up the way you did last year with the combinations. And Lizzie said, weren't there a lot of them? Because you had to say if it was 1 or 2 or 3, and then it had to add them. We're going to eventually do that and make tables for those. So, I mean, that's coming as long as you can see that these are all a little bit different. So, good job. Okay, so let me give you a little work to do. And you did most of it, so it's just a little bit left. All right. Okay, so since you caught me on my mistake there, you have 10 minutes today and 10 minutes tomorrow.
I love it.
So you don't have to take this home. Just make sure you're working on it.
There aren't any questions on it. 34.
That is it.
I know. It's